Welcome to week 4 of IC Design for Wireless Systems. In this week, we will start the receiver design and transistor level in CMOS process. The receiver design, we are going to start with low noise amplifier. When we want to design a low noise amplifier, we need to design keeping in mind about the input matching, because the signal is coming from outside the chip. So it has to be properly matched to avoid any reflection. It needs to also have low noise while providing signal gain. Let us redraw the basic receiver we have discussed earlier. The signal comes to an antenna through transmission line. It reaches the packaged radio, and the first block will be a band select filter, and then this output goes to the RFIC, and on the RFIC there will be a low noise amplifier at the first stage, followed by quadrature mixer, which is also fed by an oscillator, and this quadrature mixer generates I and Q signals. And on these blocks, we already know there will be a channel select filter followed by a variable gain amplifier and an ADC. So now we have got some idea about this interface. This first stage band select filter is generally not on the RFIC. When the signal enters RFIC, first stage it is going to see is in LNI. So now we are going to see how to design an LNA and what kind of specifications and trade-offs are present in such a design. We need to understand a concept of noise figure from a signal chain when you have multiple noise generating blocks present. But this is what we are also going to see in regular receiver. So let's take a very simple example of 3 stages, and each of the 3 stages are generating their own noise, and they have a corresponding voltage gain also. And this cascade of 3 stages is driven by a source Vs, which has a series resistance of Rs. We want to understand what is going to be the overall noise figure of such a cascade. So to understand that, let us start with the known formula for noise factor. We know noise factor is SNR in by SNR out. Now in this example, we can see that the SNR in is power of this signal divided by the noise of Rs. So Vs is the RMS value. So it is going to be Vs square divided by voltage noise of S. And similarly, we can also write the SNR at the output. So SNR at the output is going to be net signal available at the output and the total output noise. So this is going to be Vs square multiplied by A1, A2, A3 whole square. That is the signal power at the output, divided by total output noise. Let me just call it VNO. So if we simplify this, see that this Vs actually gets cancelled. So this noise factor, if you see properly, doesn't depend on the amount of signal which you are applying. And that also makes sense because the noise factor is the property of the system and it should not depend on the signal strength. If you rearrange, it becomes the total output noise divided by A1, A2, A3 square multiplied by the noise due to the input source. So if we look at this expression in the denominator carefully, we find that this A1, A2, A3 whole square multiplied by the VNS square is actually the noise of RS, which is appearing at the output after passing through these three gain stages. You can write the noise factor as total output noise divided by output noise due to input source. This relationship is going to be very useful whenever we are trying to find the noise factor or noise figure of a system which has multiple stages involved. Now let us try to find out what is the noise figure of these three stages of gains cascaded. So using this relationship, we can write noise factor as total output noise divided by noise due to input source. The total output noise is going to be noise due to RS, which is appearing at the output due to VN1, VN2, VN3. Due to RS is going to be VNS square into A1, A2, A3 whole square plus noise due to first stage Vn1 square A2, A3 whole square Vn2 square A3 square plus Vn3 square divided by output noise due to input source, which is Vns square A1, A2, A3 whole square. We can rewrite it as 1 plus Vn1 square divided by Vns A1 square plus Vn2 square divided by Vns 1 by A1 A2 square plus Vn3 square divided by Vns square to 1 by A1 A2 A3 whole square. If we look at this expression carefully, we can see that this is the output noise at the first stage and this is the output noise at the first stage due to the input source. So this rewrite it as 1 plus Vns square A1 square plus Vn1 square minus Vns A1 square divided by terms. So what I have done is in the numerator I have added and subtracted this extra term so that we can easily recognize this sum of the two noises, nothing but the noise due to the input source at first stage and the noise due to the first stage itself. So this is the total output noise at the first stage output divided by the output noise at the first stage output due to the input source. This is from our definition same as the noise figure of first stage, and then we get this term which is divided by the same. We get this 1 plus f1 minus 1, and if we extend this same technique, we'll find that we get this f2 minus 1 divided by a1 square plus f3 minus 1 divided by a1 square a2 square. Cascaded noise figure has the noise figure of individual stages, but each of the stages, their noise factor is appearing with some scaling depending on the gain of previous stages. So for the second stage noise factor, it is kind of reduced by the gain of the first stage, whereas the noise factor of the third stage is reduced by the gain of first stage and second stage. This is also called as the cascaded noise factor. And the important conclusion here is, so this 1 and 1 will get cancelled. So the noise factor of first stage appears as it is in a cascade. Second important point is impact of noise from succeeding stages is reduced by the gain of initial stages. Takeaway message is, if we are having such a signal chain with multiple stages, it is good to have a first stage which contributes very low noise. So inherently it has a very low noise figure, as well as it should have a high gain so as to desensitize the impact of noise from the succeeding stages. And this is the motivation behind using a low noise amplifier as a first stage in a receive chain. Before starting the design of an LNA, let us briefly discuss the noise which are present in a MOSFET. So let's say there is an NMOS which is biased above threshold voltage at the gate side, and the drain is connected to a battery VDS. Let's then observe the IDS. So we know that this IDS depends on the region of operation. So in the linear region, we know a MOSFET acts like a resistor, and since it acts like a resistor, we also expected this MOSFET to then has a thermal noise just like a regular passive resistor. So the linear region, IDS is equal to mu and Cox W by L, VGS minus VT, VDS minus VDS square by 2. So at low VDS, we can define an R on equal to VDS by IDS as 1 by mu n Cox W by L VGS minus VT. Let's call it 1 by GD naught. So the incremental conductance at VDS is equal to 0 is going to be equal to mu n Cox W by L VGS minus VT. So it means we can expect a current noise PSD corresponding to a resistance of this value. So if I have to write the drain noise due to this thermal noise, it's going to be equal to 4 kT by R on. This is in ampere square per hertz. This is the drain current noise PSD due to thermal noise. We can rewrite this as PND thermal is equal to 4 kT CD naught. So we can also talk about thermal noise in saturation. When VDS is greater than VGS minus VT, MOSFET is in saturation region. Then we know the IDS is going to be equal to mu n Cox W by 2L VGS minus VT whole square. So ignoring the channel length modulation. Here if we see that there is no drain source voltage dependence in the IDS. Channel is present even during saturation region. So this channel resistance will contribute to the rise in drain current. So even though the RDS looks infinity, but this channel resistance is going to add noise. So it means if we have to see the drain current noise PSD due to this channel resistance, it's going to be equal to 4 kT divided by R channel. And this channel which has been formed for a given gate source voltage, its resistance will be more or less same as the resistance we have found in the linear region. Because if the gate source voltage is not changed and only the drain voltage has been changed so as to change the region of operation, you don't expect the channel resistance to change significantly. Equal to the 4 kT into channel conductance, which is equal to mu n Cox into W by L VGS minus VT. And in reality, we see that this channel may have some change in the profile because of this extra VDS voltage which has been added. So the net result is the thermal noise in the drain current saturation region may not be just corresponding to 4 kT into the channel conductance, which is found at the case when VDS was 0, but some extra factor gets added. That factor we call as noise factor. So if we look it closely, we can see that this expression is actually the GM of the transistor when a gate source voltage or VGS is applied. So we can rewrite it as 4kT gamma GM. Thermal noise in saturation region is also very similar to the noise which we have seen in the linear region. Just that we have replaced the GD naught with this gamma GM, where gamma is the noise factor and it is equal to 2 by 3 for long channel MOSFET. As we go towards more advanced technology, where the channel length becomes shorter and shorter, this number is found to increase, and it is for many processes it is almost equal to 1. The noise in a MOSFET can be modeled as a noise current in parallel to the drain source current. So the total current is going to be IDS plus IND, where this current source is modeling the noise and it has a noise PSD of IND. Okay, if you plot the noise PSD as a function of frequency, as per our discussion, this is only thermal noise, so we expect that if the MOSFET is biased in saturation, it will be having a flat frequency response for the noise current PSD, gamma GM. Now this is the expected noise current PSD, but in reality we see that as you move to very low frequency, this noise current PSD is not flat and it starts showing a 1 by F kind of behavior. And this kind of behavior is seen. The reason is at very low frequency, another type of noise starts dominating, and this noise is called as flicker noise. Whereas this, call it as INDF, see that it is proportional to 1 by F. This is also called as flicker noise. Even thermal noise is going to be present at low frequency, but it is going to be much smaller compared to flicker noise. IND has two components. One is thermal plus this flicker. And experimentally, it has been found that this flicker noise inversely proportional to the frequency. In addition to that, it also depends on the area of the MOSFET and Cox, which is the capacitance per unit area of the MOSFET. Now the origin of this flicker noise is because of some defects in the interface between the channel and the oxide. So if you look at the cross section of a MOSFET, let's take an example of a NMOS. This interface, which is present between the substrate and the oxide, this interface is having many defects. Because of these defects, when electrons or holes are flowing in this channel, and randomly they get trapped and then released. So because of this random trap and release phenomena, we see fluctuation in the drain current, and this noise is having 1 by f kind of frequency response. Apps in silicon interface. Turns out that if we refer this noise current towards the gate of the MOSFET, for example, this flicker noise, I can model as a separate noise PSD. This is also possible to be modeled as an equivalent gate voltage. GF PSD of this equivalent gate voltage modeling the flicker noise is equal to constant divided by F L Cox. So many times it is convenient to model the flicker noise as an equivalent gate voltage. As we can see that there is no bias dependent term here, whereas when it is referred to the current side, this flicker noise will also depend on how the MOSFET is biased, mainly what is the transconductance of this MOSFET. This is noise. Here we have thermal noise. And one more point to note here is at some frequency, this flicker noise is going to be equal to the thermal noise. This frequency is called as 1 by f noise corner frequency. And this is an important frequency because it tells you if you are operating at a given frequency whether you should be worried about the flicker noise or not. We will see that in the latest technology notes, CMOS process. This 1 by f noise corner frequency will be somewhere around a few hundred kilohertz to 1 megahertz. So if you are operating, let's say, around few gigahertz, most of the time you can ignore the flicker noise unless you have done some frequency translation where this flicker noise is also going to come into picture. So this flicker noise corner around megahertz. So now that we have got some basic idea about noise present in a MOSFET, so let us try to design a low noise amplifier for our application.